We next discuss surface integral or in physics we use the term flux. Let us consider a vector field and the corresponding vector is F. So this is a region at each and every point of which this vector F is defined. Consider a vector field vector F. In this region where vector F is defined, let us consider a surface, say S. This surface S may be an open surface or maybe a closed surface, whatever. Consider a surface S, open or closed. Let us divide this surface S into small subsurfaces or small portions. So this is the first portion, second portion, third portion, and this is, say, the ith portion. Divide S into n small subsurfaces or portions, and let us call the ith subsurface delta Si vector, because area is a vector where I is equal to 1, 2, 3 up to n, and vector delta Si can be written as delta Si into Ni cap. This area is delta Si, and let us trace the contour of this area or surface, say in this sense, the anticlockwise sense. Then the unit vector which is normal to this surface is, say, this one, where Ni cap bears a right hand screw relation with the sense of traverse of this contour. With sense of traverse. Here one thing is to be noted. For open surface, we can trace the contour in any way we like. If it is anticlockwise, then Ni cap is up above. If it is clockwise, then obviously we will take the unit vector downwards, so that right hand screw relation is obeyed. But for a closed surface, it is conventional to consider the outward unit vector. This Ni cap has to be the outward unit vector, and therefore tracing of contour has to be in the anticlockwise sense. Let us write this as a note. For closed surface, Ni cap has to be outward unit vector as per convention. This has to be remembered for a closed surface. Since this is a field of F, so at each and every point there will be a definite value of vector F, and hence at the location of delta Si there will be a value of vector f also, and let it be vector Fi. So this is the value of vector f at the location of delta Si. We now construct the scalar product or dot product between vector f and the surface elements. So if this is the first surface element, then we consider vector f1 delta s1. If this is the second one, vector f2 delta s2, and for the nth one, let us now add them. Adding, we get this is the ith contribution, and we have to sum from I equal to 1 to I equal to n. I equal to n. Let us take limit n tending to infinity, which means number of such portions or surface segments is infinite. In other words, the size of the segments reduces to 0 in the limit. So under this condition, we have by definition in this limit, this area segment is no longer finite but is infinitesimally small. So delta will be replaced by d and summation will be replaced by integration, because now under this limit we cannot perform the sum. In this limit we cannot identify and count the segments as 1, 2, 3, etc. Things are continuous and summation is replaced by integration sign. So we have for open surface and for closed surface we have to put this loop sign. Alternately, this can be written as and we have to be careful that this n cap represents the outward unit normal at the surface element vector ds to closed surface S. This is called the flux of vector f over S, or the surface integral of vector f over S, and this is called the outward flux of vector f over the closed surface S, or the outward normal surface integral of vector f over S. Let us write all these things clearly at one place. Flux of vector f over or across S is This is also called the open surface integration of F over S. And in case of a closed surface, the flux is and this is closed surface integral of vector F over S. This is also called the outward flux of vector F over S. So this is very important for a closed surface. Let us next consider the application of flux or surface integral in physics. First application, let us consider a region where there are some mass points or point masses. In this region, let us consider any closed surface and let us call it S. These mass points or point masses create a gravitational field and let us denote it by vector E. So what will be the flux of vector E across the closed surface? This is given by Gauss Law of Gravitation. Which states that the flux of gravitational field vector E across the closed surface S will be minus 4 pi g into the mass enclosed by S, where g is the universal constant of gravitation. The value of which is and M enclosed is the mass enclosed by S. Second application of flux. Let us consider a region where several discrete charges are distributed. So these are point charges and they create an electrostatic field denoted by vector E. So what will be the flux of vector E across a surface, say S, a closed surface imagined in this region? This is given by Gauss Law of Electrostatics. According to which the flux of electrostatic field across the surface S is equal to 1 by epsilon 0 times the total charge enclosed by S. Here epsilon 0 is the permittivity of vacuum equal to 10 to the power minus 9 by 36 pi farad per meter, and Q enclosed is charge enclosed by S. Another example, if Gauss law of electrostatics gives the flux of vector E across a surface S in the electric field region, what will be the flux of magnetic induction across a surface in a region where there is magnetic field? And the answer to it is given by Gauss law of magnetostatics. According to which the flux of vector B, the magnetic induction across a closed surface, is 0. Here B is magnetic induction. We have therefore shown three applications of flux or surface integral. The surface integral or flux of gravitational field over a closed surface is given by this expression. The flux or surface integration of electric field over a closed surface is given by this expression, and the flux or surface integral of magnetic induction over a closed surface is 0. We next define what we mean by volume integral. Let us consider a region of space where at each and every point vector f and a scalar f are defined. So this is a region which we may call vector f field or scalar f field. So we consider a region where these are defined. This is the vector field, this is the scalar field. In this region, let us consider a volume, and let us call this volume V. And let us divide this volume into small subvolumes, and we divide them into n number of subvolumes. The ith subvolume is denoted by delta Vi, where I runs from 1 to up to n. And let us show the ith subvolume. Say this one is the ith subvolume. This is the first one, second one, third one, the nth one, and the ith one is this one. At the location of this ith subvolume, that is at the location of delta Vi, let the value of vector f be vector Fi, and the value of the scalar field F be Fi. So these are the values of vector F and scalar F at the location of delta Vi. Let us consider or construct the products as follows. In the first subvolume, the value of vector F is F1. We multiply it with the amount of the subvolume, say delta V1. For the second volume element, we thus have vector F2 delta V2 and so on. The last one, that is the nth one, is similarly for the scalar field. So with the scalar field, let us construct these products. Obviously, these are simple multiplications, neither dot product nor cross product. Therefore, dot or cross sign should be avoided. Let us add such products to get. Let us write the ith one first and then sum over I from 1 to n. And here 2. Then take limit. So that the subvolume tends to 0 in the limit. So in the limit, we are left with, from this one, this is by definition where this finite volume converts into volume element which is infinitesimally small, and since counting is no longer possible as n is infinity, summation is replaced by an integration sign. From this one we similarly have these are defined as volume integral of vector F over V, or in this case of scalar F over V. We now mention application of volume integral in physics. Consider a region where there is matter or mass and an elemental volume dV contains mass dm. So dV, volume element, has mass dm. So the mass density is this is mass per unit volume, and it is defined as mass density and denoted by the symbol rho, say. So dm is rho dV, and the total mass is total mass is the volume integral of the mass density. Next application, consider a region where there is charge and let this dV volume element contain a charge dq. So dV has charge element, say dq. So the charge density is which is denoted by rho. So dq is rho dV and the total charge is q integration over v of dq, which is therefore the volume integral of charge density. Clearly, the concept of volume integral is needed to find the total mass or total charge in a region of space.